Anyone an idea what's shown in this picture? Memory, that's one. I see more things there. CPUs, indeed. Sensors. So basically we have all kinds of computer chips in our lives, and these are just some examples. And in this session, basically I'm going to explain how these chips are created, how we make sure we get as many functioning chips as possible, and then how Java is involved, because I mean, it's a Java conference, right? So I need to tell something about Java. My name is Johan Janssen. I'm a software architect at ASML. I'm not trying to sell you anything. Our machines are way too expensive for you. And if you think you can buy one, hit me up. So sensors, this is a bit of marketing, but to give an impression, like how many of these computer chips do we use in our daily lives? It's a lot. I mean, each computer or each car is already filled with all kinds of sensors and other processing units. Oh, not that quickly. And they expect, apparently, that in a few years, we have 41 devices each person. I don't hope we need to carry that, because, I mean, I need bigger pockets, and a huge amount of data. Anyone idea what this is? A wafer. What's on the wafer? The Duke, indeed, the Java mascot. So basically, this is a wafer, and computer chips are created on top of this. And this is about the same amount that you normally have. If you have processors printed, this is like 564 Dukes. You can count them if you want, or believe me. That's more or less the amount of processors normally are printed on a wafer. If it's sensors or smaller stuff, it can even be thousands. And the basis for that is a transistor. So a transistor looks like this, at least in the past. Nowadays, you cannot really see them anymore. They're so small. And it works like a water tap. Water flows in, you can control it, and then more or less water flows out. Transistor does the same, but then with electricity. And the really interesting thing, and I mean, most of us probably know the law of Moore. You can explain it in different ways. The most common way is to say the number of transistors doubles every 2 years. It's a bit weird, right? Which other industry doubles every 2 years? Are cars getting twice as fast every 2 years? Are houses or flats built twice as high every 2 years? I don't know any other example where it happens. But for some reason, for transistors, it's already going on since 1970. And they still sort of manage to keep that growth going. So it's an insane amount of growth. So they get smaller and smaller. And when we talk about small, so at ASML, we talk about nanometers or even smaller than nanometers. And 1 million nanometer is 1 millimeter. I couldn't really understand that. It's just really small, right? To give some examples here, I put some stuff in nanometers in here. Any idea at what level of detail, how many nanometers accuracy we print nowadays with our machines of ASML? I hear 1, 4, it's more or less in between, it's 2 or 3 nanometers. So it's really small. It's going towards atom size, basically. It's incredibly small. Why do we want to print it that small? Imagine Lord of the Rings, maybe you read it, maybe you watched the movie. It's 1,100 plus pages. Costs a lot of paper. If you print it on 13 nanometers, which is relatively big, you can print it on one slice of A4 paper, 2,625 times. So it's way cheaper to move it. If you produce it in another country, you can put a lot more in a shipping container. Of course, you need some way to read it. It's really small then, but hey, that's a detail. But it's the same for chips. The more memory we can print on the same surface, the better. The more transistors and the faster CPU, the better, basically. And it also makes the smaller the transistor, the less the power consumption. So also from power consumption perspective, there's a big advantage at going smaller. It all starts with this, silica sand. It's sand that's available in abundance, and if we ever run out of it, we can always excavate the golf courses, because they also use it, the white sand you see there. So if you ever see them excavating it, it's probably about time to buy your new computer, because afterwards it will be really expensive. Yeah, without kidding. So then from that sand, it's basically melted, really high temperature, and they create something like this. It's called an ingot. Really weird shape. Apparently it's because they put it in some basically liquid and turn it around and then pull it out. That's why it has this weird shape. And from this ingot, wafers are created. So here you see an example. This is called a front opening universal pot, or FOUP. This is basically used to transport wafers across the factory. Because mostly we don't transport them one by one. We put them in things like this and then transport them to a machine, and then the machine one by one does whatever it needs to do. To give you an idea on how fast these things work, so depending on the machine, you can print about 330 wafers per hour per machine, but that's just a single layer. For some chips, that can go up to 200 layers that need to be printed on top of each other. I mean, the amount of transistors per square millimeter, I mean, it's insane, right? You cannot really imagine it. It's really huge. And then it goes a little bit like 3D printers. Maybe you tried a 3D printer in the past, but probably you saw a video or something of it. It prints lines on top of each other, and then you get whatever you want, basically. We do that as well, something comparable, but the accuracy is a little bit different. We talked about 2 nanometers. To put that in perspective, let's imagine you drive across a road for 300 kilometers on this line. You turn around, drive the same 300 kilometers back without deviating more than 2 millimeters. That's the accuracy we're talking about, to put it in real-world examples. So, yeah, really small. Then those wafers, they go into this machine, which puts coating on top of it, called photoresist, or sometimes called resist. It's some chemicals put on top of the wafer. And that will be used as the basis for the printing. Now the wafer's coming back. Let's go to the next one. And then it goes into this machine. So this is basically what's called a lithography machine. It's a really huge machine. Has hundreds of thousands of components. Requires 3 Boeing 747s to transport it, and a really huge amount of trucks. So this is basically the heart, what most people see for chip manufacturing. Then that wafer is placed on a magnetically levitating wafer table. Really, it's a mouthful. Basically means we use magnetic stuff to keep the wafer floating, because if we clamp it, it will bend a little bit, and that bend will result in less functioning chips. So it's really, it needs to be really accurate. This then, and so this has the resist on top of it, the chemicals, and then we need to print basically with light on those chemicals. So I'll show you how that works. Basically what you saw here is the wafer, the laser, which is placed underneath of the lithography machine in the basement. It's just as big, basically. It's a laser amplifier. It amplifies until 40 kilowatts, and yeah, it's almost the strength as some countries use to shoot planes out of the sky. It's one of the most powerful lasers, and they shoot at droplets of tin, as you saw in the animation. And so it hits the droplet of tin twice, once to make it a pancake, then the second time it hits it hard, and then plasma is basically emitted. And that happens 50,000 times without splattering the entire machine full of tin. I found it remarkable that they even managed to do this once, but even it ran in production, apparently. So this is how it works. This is not a UFO. This is like a video which they created in super slow-mo, where you can see it be hit once and then hit the second time. And then it results in plasma. Plasma comparable qua heat as the surface of the sun. So special gases are then used to make sure the temperature decreases. And that plasma basically emits EUV light. And yeah, our current newest machines use EUV light, which is quite a brittle light. It goes away quickly. So we need to do a lot of precautions to make sure it still exists and doesn't vanish. For that we use mirrors. These are some of the flattest mirrors you can find. They have about 100 layers of special material. And if you would basically stretch this one to the size of Germany, the highest bump is 1 millimeter. So they're really flat. And that's then put basically in the machine. So here you see, you see it coming out. Here you see the different mirrors. And here is the so-called reticle, which we will talk about later. And in the end, it comes here to print on the wafer. So what's that reticle? It's a bit like a template or a stencil. You probably used it in the past, something like this. Maybe you still use it. If you draw on it, you can only draw on the open spaces. With a reticle, it's the same. Light shines through the open spaces, and where there is no open space, no light shines through. So that way we create a pattern on those chemicals that are on the wafer. So a reticle looks like this. It's a bit more expensive than the template that you're using at home. So how does it work? Basically, the wafer stage, which contains the wafer, and the reticle stage, which contains the reticle, they move in opposite directions, but then with an insane speed. So the reticle moves at 15G and the wafer at 5G, while still being able to print in the right direction. And to do that, basically the position of the wafer, we already put it in the right position before we start printing, but even during the printing, it's basically adjusted 20,000 times per second to make sure it's in the correct position. And then it looks like this, basically, the reticle part. And then it goes like this. So on the left, you see the machine with a wafer. Here it's basically measured so that the position is okay, and the one next to it is doing the printing. This basically speeds up the process, because otherwise we need to wait until it's positioned properly before we can start printing. So that's why we do 2 wafers at the same time. And then it goes like this. So at the top you see the reticles being changed. At the bottom you see the wafers being changed and the printing going on in the machine. And here you see one of those FOUPs. So yeah, this is in short how the EUV machine works. And to explain how it works with the EUV light, so we have the wafer, we have the resist on top of it, we have that reticle with some light shining through and other not shining through. And then we can determine to keep either the parts where the EUV light has shown on, or remove those parts. And with that we create transistors and layers. Yeah?
There was a sentence on a slide, a couple slides back, about why the mirrors was used. But I didn't have the time to read it, but I'm wondering why the mirrors.
Good question. So you ask why mirrors are used. In the past we used lenses, but if you use a lens, the EUV light disappears. So previous generations of machines worked a little bit different. With EUV, they had to almost change everything to make sure that that light doesn't disappear. Yeah, good question. Yep. So I shown a small part. It's a way longer process. So you see here, for example, the photoresist. We saw that. The exposure, the printing, we saw that. But then it's also developed and bake, etching. We remove stuff. All kinds of processes involved, and multiple machines. So you saw the printing machine. Applying the photoresist is another machine, measuring, which is shown at the top, or other machines. So there's basically a whole set of machines involved from different companies to create it. And then this circle is basically executed for each layer. So if we have 200 circles, 200 layers, we have 200 circles. Here, this comes back to your question. So before we had DUV systems, now we have EUV. Lenses versus mirrors is one of the differences. One of the other reasons that we now use EUV is that to print some features in DUV, we needed to print multiple layers for that feature. With EUV, we can print that feature in one layer, so it's way quicker, saves cost, things like that. The interesting thing is that maybe you would think, okay, now we have EUV, so we throw away all the DUV machines. That's not the case. For some critical parts, EUV is a must-have, like the latest chips you use in your smartphone or in your laptop. They use some EUV machines. But some of those layers can still be printed with DUV machines. For example, the connection layers that are less critical, they can be created by different machines. So one layer may be created on one machine and the other layer may be created on another machine. And actually, from all the machines that we sold in the last 30 years, 95% is still up and running. The really like old ones, you can simply use them for sensors or for computer chips for your refrigerator or something like that. They're still valuable. Of course, we try to upgrade them, maintain them and everything, but they're still up and running. And then you get wafers like this. But also, let's have a short look ahead. So, the future, near future, you see 2024, we are going towards the new generation of machines. And yeah, I don't know, nowadays, with continuous delivery and having releases every 5 minutes, we are used to having a lot of releases quickly. These kinds of machines, they take 10, 20 years to develop for a generation, basically. So it's not as fast as you might imagine. So this basically makes sure we can print even smaller, we can still follow that Moore's law and continue with further development. So what is changing there? What's changing is so-called numerical aperture. And what's that? It's basically how well you can focus the light. So this is an example of our old systems. So this doesn't show the high-NA systems, it simply shows what numerical aperture is. So let's say on the left, you see some of the light bouncing back. That's not what we want. We want all the light in the bottom. So we found out if we put water in between the lens and the wafer, the focus is better. So in that way, we increase the numerical aperture. So our new generation of machines will do even fancier stuff to increase the numerical aperture. So how do they do that? New mirrors. The old mirrors are about 100 kilograms each. The new ones are more than 1,000 kilograms each. So it's insane. Where I told you before, the mirrors, if you stretch them to Germany, it's 1 millimeter bump. Here we're talking about stretching it to the earth with like a thickness of a hair of a bump. So they're way more advanced as the old generation. And what you probably already guess from these big increases is that each generation our machine also gets way bigger. Which is interesting because we try to print smaller stuff, but everything around it gets bigger. And here you can see the speed from the old and the new ones next to each other. So left is old, right is new. So this is basically what's coming in the coming years. This is how the reticle moves in the new situation. I thought it's one of those funny movies where at the end it flies out, breaking everything apart. But apparently this one moves at 32 Gs continuously without breaking, which is insane. And we expect more and more measurements. We already have a really large amount of measurements, but software is becoming more and more important. The smaller the details printed, the closer we get to hardware limitations, the more important we need software to make sure that we have the best chips. We expect really billions of measurements in the near future. So yeah, we have chips, but how do we make sure we have a lot of them and a lot of working chips? We start with a really clean room. So you see those people from NASA? Pretty dirty, right? Then you see a clean room. It's super clean. The biggest contamination is a human. So if you go in as a human, they have measurements, you can see the number of particles in the room go up. And that's, of course, with ventilation and everything, they try to regulate it. But yeah, humans are the biggest contamination. You are, for instance, not allowed to wear perfume when you enter one of these rooms, because that already contaminates it. It's so small. But then what can go wrong? Let's imagine we have one layer, we look at it from the side. I'm not really good at drawing, so this was the best I could do. We have the second layer. It's slightly off. I mean, you can see that. So this is not really good. We try to prevent this. But of course, I mean, one of the things you need to realize is when I say prevent, it sounds easy, but with such a difficult machine, with so many parts, if only one is slightly off, you already can see things like this. So you almost have to expect that this happens. It's not that we prevent it from happening, we try to find it as quickly as possible. If this goes through, you can have a concept called fallover, so then the lines fall over each other, not something you want to have. You can also have something like this. It's also not really good if it doesn't make a connection or even connecting two layers, having some form of short circuiting. And there's a lot of these kinds of problems. Some of these problems are annoying, but you can do something with it. Let's imagine you have a 32 gigabyte memory that you are creating, and one part doesn't work. Depending on the chip design, they can disable one side and sell it as a 16 gigabyte chip. So it's not worthless, but they earn less money with it. So you can still use it, but customer wants to have the full ones preferably. And so you have a lot of these kind of defects, and there are basically two other categories how you could look at it. Is you can have issues on one wafer, so let's say a dust particles on the wafer, then maybe some chips are broken. But if there is an issue with the reticle or with the laser, then every wafer that goes through has an issue. And that's of course a way bigger issue than just one wafer, a few chips that break. So how do we look at that? Basically, you have two kinds of measurements. One is looking on a single layer to see, okay, is this layer printed the way we want it to? And the other one, it's called overlay. I think that's the easiest one and the most common one that most people involved know. That's basically checking if two layers are on top of each other. The simple one, which I showed with the lines. Then what we do, we have basically two types of machines to measure this, because you cannot put it under a microscope. It's too small for that. So we have diffraction-based and E-beam measurements, and one measures the overlay, the other one measures the critical dimension. So how does that go? This is an example of a machine. Again, you see some FOUPs with wafers in it. And this is the inside of one of the machines that basically measures how well everything is going. Here you see different colors of light being used. They send the light to the wafer and then it bounces back. And based on the diffraction of that bouncing back, they can see if a layer is properly aligned or not. It's all kinds of special algorithms, of course. So this is one of the ways how we can measure the quality of one of the next layers that we printed. So we get a lot of these things in. So for example, we saw that wafer table. When it's printing, it still measures 20,000 times a second. Each machine produces 31 terabytes of data, and most of our customers have a lot of these machines. And basically, we use them to do all kinds of algorithms to determine, okay, what needs to be changed to make the next set of wafers even better. And then we recalibrate the machine, basically. And each machine has 100,000 parameters which can be configured. So to give you an example, we have this. It's called a mirror, but I find it a bit weird because it's actually 4,096 mirrors, and they can all be controlled individually. So if there is an issue, they can configure one of them to move slightly different or use a different angle. So this is just one of the things we can control. Angles of mirrors, etc. If the temperature of a laser gets too hot, we could emit more gases to reduce the temperature, etc. There's a lot of things that can go on. All that data, both from the lithography machine, so the one we saw before, which does the printing, and these metrology machines and other machines, is combined into a platform. So there's a lot of data going in, and the end result should be recipes, as they call it, to recalibrate the machine for better performance. Our software is, from our side, really secret. Some of the stuff is patented. Some is even more secret that we don't even want to patent it. So we don't really want to share it. On the other hand, we have our customers that have data, which is really crucial. If their competition would get that data, they could use that to improve their machines. It sounds weird, but yeah, what some of these guys do with data and see in the data is quite a miracle. I show a screenshot later, and one of my colleagues thought he saw customer data in it because he recognized the patterns. It wasn't customer data, but I was quite scared that he recognized the customer based on a pattern. It's there's a lot of automated stuff, but also some really smart guys and girls working with these kind of things. So these are big servers that we use on-premise, where we store the data from the customer on-premise at the customer. And yeah, at first I thought, oh, it's a server, probably a server rack like this, but apparently it's hundreds of CPUs and hundreds of gigabytes of memory for each cluster that we install at the customer. So it's pretty big. So what do we do with our tool? In the past, we had a lot of different tools, and they looked different, they couldn't share data, and those tools, they are used by customer support, so my colleagues, and by customers to work with the machine, basically. So we want to make it as easy as possible and as fast as possible. And that way, we created a platform, but we had a challenge. One, if you create a platform, you want to make stuff generic, because that's easier to maintain. So we created parts generic. Like if you store data, a wafer ID is a wafer ID. It's almost used everywhere. Same for the machine ID. It's almost used in every analysis. But there are also a lot of differences. Like some of the measurements that are done, they produce plain data, plain text. Other ones produce images. So we need to be really flexible and basically support any scenario that our customers or our colleagues want to build on top of it. A bit like a train platform. You mean you have one platform that can accommodate small trains, big trains, fast trains, slow trains. We sort of try to do the same. So how does it work in the more technical part? So we use Spark. With Apache Spark, it's really easy to distribute workloads. So it's especially well suited if you have large amounts of data or processing algorithms that take quite a long time to process. And basically works this way. You have worker nodes, which are basically different machines. And all the data is sent to those different machines. Processing happens there. Results come back to the so-called driver, the main application, and there you combine it. So that way you can do really large amounts of data, the terabytes of data, while still having proper performance. Of course, I mean, if you do this Spark stuff is really advanced and really cool, but it has a bit of a learning curve if you want to do some more advanced stuff with it. But yeah, we basically needed it, so we invested in that. On top of that, we created 3 types of plugins. First, a data plugin. We need to import data into the platform. So every department in our company, they can create these plugins, and we plug them into the platform. They import their own data. They can create UI plugins to visualize data in a way they want. Maybe they want to have graphs, maybe they just want to show numbers or errors or whatever. And we have processing plugins. So a processing plugin is triggered from the UI. So you select which data you want to analyze, you select which algorithms you want to run, and then the processing plugin is basically triggered. So it looks a bit like this. We have a React front end, a Spring for that part, which is just behind the front end, the Spark stuff, which I've shown. Neo4j to store data, more the metadata that's being used. We also use other stuff. I'll show it later as well. It's in here as well. I see MongoDB for the backend for front end. So a lot of tools that we use. Not a complete list, but these were the bigger ones that we quickly could come up with. So basically, we use anything that's available and that we can use from the Java ecosystem. Yeah, I talked about Java, so the entire platform is basically written in Java. But the interesting thing is that if you look at the departments within our company that create those plugins, most of them are not Java developers. We have a lot of developers, I don't know, like 5,000 or something in that area, and a couple of hundred Java developers. And we can, of course, force them to rebuild everything in Java. Probably good for our job security, right, and for your job security. But management wasn't too happy with that. So basically, we made a way to integrate it. So we are able to still use those languages, run them in a container, or access them via JNI. We have all kinds of different solutions to interact with those languages. So basically, existing solutions can be used on top of our platform. And there is like some adapter layer, the processing plugin in between it. So it looks like this, for example, with Julia. For the ones that don't know Julia, it's seen as a bit easier alternative to C. It's a lower level language, basically. So yeah, then the left part is still written in Java, but it communicates either via JNI or via Kafka messages with container run applications. Nowadays, machine learning is really hip, right? We all use ChatGPT. But I found an interesting example from one of my colleagues who's running these kinds of algorithms. And what they did is they scanned a wafer, and with a default scan, they could capture almost 70% of the defects. That's nice, but it's not 100%. So what they did is they slowed it down. I mean, the slower you... Oh, what's happening here? That's probably the slowing down part. So if you slow it down 8 times, we can capture 100% of the defects. But slowing it down 8 times means we cannot scan all the wafers. Basically means we can scan 8 times as less wafers. So then we might miss issues on those wafers. So it's basically blocking the throughput. We can create these layers faster than that we can analyze them. So if analysis becomes a bottleneck, creation also is hindered by that. So what my colleagues did is they used some deep learning, And with that, they managed to enhance the image and capture 92% of the defects. It's not 100%, but it means that we can still process the same amount of wafers. So this is all possible on top of the platform. You can do with it whatever you want. And to facilitate that, we created a toolbox. So we created stuff like Maven archetypes, of course, documentation. We have weekly meetings with plugin teams. In the beginning, that was a bit awkward. You have one plugin team to interact with. But nowadays, we start to get dozens of plugins. So it's becoming a really big community. And it's really new. So since I think this year we're running it at customers, it's a really new platform. And yeah, the first results are promising. And to give you a bit of an impression, I always, if I see a demo or something about a project, I always wonder like, hey, is this built by 2 people in a basement or is it an entire company? For this platform, we work on it nowadays. It's scaled up during the 2 or 3 years we're building on it. But nowadays, it's about 150 people, including management and things like that. It's not 150 developers, but it gives you a bit of a rough idea. And that's only for the platform. The plugin teams, those are separate teams. So there's a lot of people involved. And then you get this, which probably you now are confused. At least I was confused when I saw this. It was like, yeah, it looks nice, but what is it? So like I mentioned, some of my colleagues, if they see something like this, they immediately know what's going on. After a lot of talking with colleagues, I found out some of the stuff, so I can explain a little bit. So CE, that's correctable errors. We love abbreviations. So a correctable error basically means it's something where we can adjust the machine so that it doesn't happen the next time. So if you look at the top left, we see all the arrows pointing in the same direction, like this. If we now recalibrate the machine to print a little bit like this, it's fixed. So that's correctable errors. On the left side, we see non-correctable errors. If you look at the length of the lines and the color, that's basically how bad it is. But this is basically pointing in all directions. I mean, if you have an arrow like this, an arrow like this, yeah, you cannot really accommodate that. But if you have more advanced algorithms, you might actually find some correctable errors in this plot. So the more advanced your algorithms get, the more stuff you can detect that you can actually fix. And then, yeah, we have some of those manual colleagues who are so good they can even manually get results out of this. So this is basically what we do. So this is one type of plot. We can plot all kinds of things. We can, for instance, compare for 100 wafers how much they deviate from each other, compare them with each other, or compare 2 machines. Basically, anything can be compared to see what went wrong and where it went wrong, if it was an issue on a single wafer or if it was an issue on the machine, so every wafer will break. So then we come to the end. One interesting thing I found is that, yeah, sometimes you hear Java's old, Java's slow and everything. But we built this platform which basically handles a really big amount of data. Needs to be really fast. And explicitly Java was chosen for it. And I think one of the reasons is for Java you have a really large community, a large set of tools that you can use. I mean, we use a lot of those tools out of the box. And if you cannot find a tool, build something on top of it. So we built some stuff, some of it is patented, some is custom. For example, Apache Spark is really awesome. It can process your stuff in parallel on different machines, but it doesn't give you a process indicator. Like if you install Windows or another operating system, you get that nice bar, and then it's stuck at 80%, and the last 20% takes the same amount. That kind of thing is missing in Spark. So we looked at the lower level Spark APIs. They provide REST endpoints, Java APIs for it, and try to build something on top of it. And then you also get a bit in the quirks of Spark. Some of the APIs are eventually consistent. So if you request them, it can be that you get nothing back, and then you do a thread.sleep and the same, and then you get data back, which is sort of annoying, right? So we didn't use those. We in the end used some other APIs. But with that, we managed to track progress and then also map it back to the concepts that our users know. Because Spark uses jobs and tasks and things like that. The users of our application have no idea about a task and things like that. So we map it back to the processes they are running and build that on top of it. So that way you can do so much with the Java ecosystem. But one thing I really want to emphasize is this stuff probably sounds cool. But like with all the conference talks, it's not a silver bullet. Don't start using all these tools tomorrow. you probably run into issues, and a lot of the things you probably don't need. And yeah, always start simple. For example, when we did communication between the systems, we first used REST, worked perfectly. After some time, we wanted to send asynchronous messages to basically improve the availability of our system. We wanted to do streaming data. So then we added Apache Kafka. So it's a gradual process. We don't start it with that entire tool set at once. We just built the most important parts and then kept evolving it. Because otherwise you're only playing with tools and with technology instead of bringing business value. So I think that's an interesting one. So yeah, still, I mean, I really like the Java part. For almost every problem, you can find a solution or a solution that at least comes near so that you can write a little bit on top of it to make it working for your case. With that, we come to the end, and I think we have plenty of time left. So are there any questions? If you're in the back, just shout, because I only see the sun there. Yes?
Yeah, there was a slide with cleanliness of the rooms. Is there any difference between the cleanliness of rooms for manufacturing machines and running them in production?
Yeah, so the question is, I had that slide with NASA and other rooms, operation room, and the clean rooms. And the question is there any difference between how clean the rooms are at basically us and at the customer? At us, they are clean. At the customer, they're even cleaner. Yeah, that's where the magic happens. Basically, there it's super clean. Yeah. Yep. Yep.
In the beginning, you mentioned a tin particle. How is that used in the process? What is it used for?
So we emit driplets of tin, and then we shoot with a laser on it. And then the tin emits plasma, and that plasma results in EUV light. And the EUV light is used to create the patterns on the wafer. Yeah. I saw a hand there as well, or no? Yeah.
How much smaller can it get until the experience quantum?
The question is, how much smaller can it get? Yeah, I hear that often. I even heard someone say, like, hey, we have these computer chip shortages, why don't you just make it smaller? Yeah, I mean, at this point in time, we are the only company that can print this small. Recently, Canon also introduced one machine based on a different principle, which they say can go such small size. But I don't think it's running in production yet. Where it stops, I don't know. I mean, next generation of machine is coming. After that, even if I knew, I probably couldn't tell you. So yeah, I think for me it's surprising that it already runs for 50 years. So I assume there is an end, but when? No clue. Any other questions? Yeah.
What are the mirrors actually used for? You mentioned they're really flat, but just a flat mirror does nothing.
Good question. So,
there was one slide that says it diminishes the light 4 times. That's not really much. So what are the mirrors used for?
So the question is, what are the mirrors used for? Maybe you can remember the picture of the machine where you had the purple light going back and forth. At the end of each light, there is a mirror. So basically, it's to direct the direction of the EUV light so that it goes in the proper direction. And I guess also to focus it somehow so that the numerical aperture becomes higher. So that's where we use the mirrors for. Basically to, make some flow through the machine. Yeah. Yes?
Did you also encounter bugs in Apache Spark while using so much data?
So the question is, did you encounter bugs in Apache Spark? Yeah, a lot. Yeah, we had issues where we ran into an issue, and I don't remember exactly what it was, but it had a one-to-many relation in our case. We Googled it, looked at the official manual, and it says it can never be something else than a one-on-one relation. But yeah, we had in our case, so somehow it was possible. So we saw some weird quirks in Spark, especially if you use the really lower level APIs. Sometimes gives a bit strange results. And also indeed with data, depending on how you use Spark, the data can be stored in a heap or offside of the heap. So you need to make sure that there's always enough memory available both in the heap and outside of the heap. And that can be quite tricky because it depends on, I think Spark has like, I don't know, 20, 30 parameters to configure that. And that can be quite tricky. So yeah, if you go with high data volumes, there is a lot of tweaking. It doesn't run out of the box anymore. But yeah, I mean, I don't think there are many other solutions that can do this scaling well. So yeah, it's a bit of a trade-off. Any other questions?
Those kind of bugs, do you create issues for them? And does ASML generally contribute to open source?
So the question is, do you report the bugs and contribute? We sometimes do, sometimes we work around it. For Spark, I don't know if we contributed. For Julia, for example, we fixed some threading issues because it didn't run properly, so we even contributed back to the language. So it depends a little bit on the use case. So for some, we found ways, for example, to work around it. And the thing for us is also a little bit, even if the issue is fixed, it's probably in the next release. And we cannot update every day because, I mean, it runs on-premise, stuff like that. We have a platform which is maintained by another team. So we cannot easily upgrade everything. So then often, yeah, you anyway need to find a workaround and maybe submit a patch for the long term or something like that. Yeah. I don't see any hands anymore. Then I would say thank you all and enjoy the rest of the day.